1953, the Cold War is closing in. America needs a shield across the Arctic, a frozen corridor thousands of miles long. But hauling supplies here, it's a nightmare. Ice destroys machines in minutes, convoys head north and fail. Engines freeze, steel shatters, tracks snap. Storms swallow entire supply lines. The Arctic is undefeated. Then one man steps forward. Robert G. LeTourneau, a self-taught engineer who builds machines bigger and stranger than anyone thought possible. He doesn't try to fight the wilderness. He aims to outscale it. His answer? A land train longer than a warship, with every wheel electrically driven, crawling like a steel serpent across snow and frozen sea. If it works, it won't just solve Arctic supply. It could rewrite how armies move anywhere on Earth. But only the ice can decide. Will this metal Leviathan conquer the Arctic, or will the Arctic conquer it? The Arctic's vast emptiness had transformed into the Cold War's most critical front line. Soviet long-range bombers could reach North America's industrial heartland via the shortest route, directly over the North Pole. This geographic reality demanded an unprecedented defensive response. The distant early warning line, a chain of radar installations stretching over 3,000 miles from Alaska to Greenland. These 60-plus remote outposts would provide the crucial 30-minute warning needed for the Strategic Air Command to launch a nuclear counteroffensive. But their construction presented an engineering challenge that would push military logistics beyond all known limits. The strategic importance of the DEW line could not be overstated. Without reliable early detection of incoming Soviet bombers, North America remained vulnerable to a surprise nuclear attack that could mirror the devastation of Pearl Harbor. Each radar station required over 500 tons of construction materials, electronic equipment, and supplies to be transported across roadless wilderness, where temperatures routinely plummeted to negative 68 degrees Fahrenheit. The environment itself became the enemy, an endless expanse of ice, snow, and tundra that devoured conventional vehicles with mechanical efficiency. The failure of existing military hardware provided stark evidence that incremental improvements would never suffice. During Exercise Sweetbriar in 1950, the U.S. Army deployed 100 new M29 Weasel-tracked vehicles, specifically designed for cold weather operations. Within 5 days, nearly half had broken down completely, exposing the fundamental inadequacy of conventional design when confronted with Arctic extremes. The Canadian Army's Penguin armored snowmobile fared no better, proving too bulky and unreliable to navigate effectively beyond established roads. The pattern of mechanical devastation repeated across every attempted solution. Standard military trucks became frozen monuments, their engines seizing and their hydraulic systems failing as temperatures dropped. Tracked vehicles, even those designed for snow, succumbed to the combined assault of extreme cold and punishing terrain, their drive systems failing under the relentless conditions. This technology crisis demanded a visionary capable of revolutionary thinking. Robert Gilmore LeTourneau had already established himself as the earth-moving industry's most audacious innovator, a man whose engineering philosophy centered on the principle that there were no big jobs, only small machines. LeTourneau's approach to engineering problems reflected both his technical brilliance and his unwavering faith. He called himself God's businessman, believing divine providence guided his industrial innovations. LeTourneau's track record spoke with mechanical authority. His company had revolutionized earth-moving with scrapers, bulldozers, and massive hauling equipment that redefined construction possibilities. Where conventional manufacturers built incrementally larger machines, LeTourneau conceived entirely new categories of equipment, embracing scale as the solution to previously intractable problems. The Arctic presented the ultimate test of this philosophy. Conventional wisdom suggested that smaller, more maneuverable vehicles offered the best hope for Arctic transportation. Multiple smaller loads could theoretically reduce the risk of catastrophic failure while maintaining operational flexibility. The U.S. Army Transportation Research and Development Command had explored this approach extensively, only to relearn the same harsh lesson: conventional logistics were failing. The environmental requirements created a precise engineering specification that no existing vehicle could meet. Any successful Arctic transport system needed immense flotation to traverse snow and muskeg without sinking. Massive payload capacity to justify the enormous expense of each supply mission, and extreme reliability in sub-zero temperatures combined with complete self-efficiency to operate far from established supply lines. These requirements eliminated virtually every known transportation technology. The Army's desperation grew as the strategic timeline compressed. The DEW line's construction schedule could not accommodate the luxury of gradual technological development. Soviet nuclear capabilities were advancing rapidly, making the early warning system an urgent national security priority. Every failed supply mission represented not merely lost equipment, but a critical gap in America's nuclear defense strategy. The entire concept of continental defense hung in the balance. Traditional military suppliers offered variations on existing themes: improved cold weather trucks, enhanced tracked vehicles, modified snowmobiles. Each proposal represented evolutionary thinking applied to a problem that demanded revolutionary solutions. The Army's search for alternatives led inevitably to LeTourneau. His reputation for tackling impossible projects with unprecedented machinery made him the logical choice for a challenge that had systematically defeated every other military transport solution. The man who had built the world's largest scrapers and bulldozers commanded both the technical vision and manufacturing capability to attempt what others considered engineering fantasy. The challenge presented to LeTourneau was elegant in its simplicity: create a land vehicle capable of hauling freight train loads across roadless Arctic terrain where every existing machine had failed. The solution would need to function reliably at temperatures that froze steel and traverse surfaces that swallowed conventional vehicles. Most critically, it would need to operate as a self-contained transportation system, independent of the infrastructure that supported traditional logistics. LeTourneau had a radical solution: a train of wheeled giants powered by electricity. But the question remained: could an electric dream survive the Arctic's mechanical nightmare? Could LeTourneau's audacious concept scale beyond the limitations that had constrained every previous attempt at Arctic transportation? The fundamental engineering challenge extended beyond mere size or payload capacity. How do you transmit power efficiently across a vehicle that might stretch hundreds of feet in length? Conventional drivetrains, with their complex arrangements of transmissions, drive shafts, and differentials, became impossibly unwieldy when scaled to the dimensions required for Arctic cargo hauling. LeTourneau's breakthrough emerged from a single recognition: traditional mechanical power transmission was the primary constraint, limiting vehicle length and configuration flexibility. LeTourneau's solution eliminated the mechanical drivetrain entirely through his ingenious electric wheel hub motor system. A diesel engine mounted at the front of the vehicle served as a generator, producing electrical power that traveled through cables to individual electric motors housed directly within each wheel hub. This diesel-electric configuration freed the vehicle from the geometric limitations imposed by mechanical power transmission, allowing for virtually unlimited length while maintaining precise power control at each wheel. The system delivered immediate torque to every driving wheel without the power losses inherent in complex gear trains. Each wheel operated as an independent traction unit, capable of receiving precisely calibrated power based on terrain conditions and load distribution. This individual wheel control provided superior traction characteristics compared to conventional vehicles, where power distribution was shackled by mechanical differential systems. The electrical power transmission also enabled regenerative braking, where the hub motors could reverse their function to generate electricity during deceleration, feeding power back into the system. The Army Transportation Research and Development Command recognized the potential of LeTourneau's concept and issued a development contract in 1954 for the LCC-1 snow train. This machine would serve as the proof of concept for electric hub motor technology under actual Arctic operating conditions. The LCC-1 stretched 173 feet in length and rode on 16 wheels, each containing its own electric drive motor powered by a single 600 gross horsepower Cummins VT12 diesel generator. The vehicle's modular construction allowed for the connection of additional cargo sections, demonstrating the scalability that made the concept so promising for military logistics. The prototype's design incorporated lessons learned from previous Arctic vehicle failures. The crew compartment featured full environmental protection, with heating systems designed to maintain habitable temperatures even in extreme cold. The electrical systems utilized specially formulated insulation and components rated for sub-zero operation. Most critically, the hub motors themselves were sealed units, designed to function reliably despite exposure to snow, ice, and temperature extremes that had destroyed conventional hardware. Greenland's ice sheet provided the ultimate testing environment for LeTourneau's electric dream. The island's interior presented conditions that exceeded even Alaska's harshness. Endless expanses of snow and ice, where mechanical failure all but guaranteed death for crew members, hundreds of miles from rescue. The LCC-1's deployment to Greenland represented more than a technical evaluation. It was a trial by ordeal that would either validate the concept or destroy it. The Army's entire approach to Arctic logistics hung in the balance, with potential implications for the DEW line construction schedules and continental defense capabilities. A successful demonstration would prove that electric hub motor technology could revolutionize military transportation in hostile environments. Failure would doom the military to rely on the very vehicles that had already proven inadequate for Arctic operations. The operational environment tested every aspect of the LCC-1's design philosophy. Greenland's ice sheet subjected the vehicle to surface conditions ranging from hard-packed snow to treacherous crevasse fields where any vehicle could disappear without warning. Temperatures dropped to levels that froze exposed metal and made human survival dependent entirely on the vehicle's environmental systems. Wind conditions created whiteout situations where navigation became nearly impossible. During its Greenland trials, the LCC-1's performance was definitive. The vehicle traversed ice fields that had stopped every previous attempt at mechanical transportation, its electric hub motors providing the precise traction control necessary to navigate treacherous terrain. The modular design allowed cargo sections to articulate independently, preventing the structural stress that had broken conventional vehicles when crossing uneven surfaces. The electrical systems continued functioning reliably despite conditions that had defeated mechanical alternatives. The crews nicknamed their machine the Ice Cap Limited, a testament to both its reliability and the affection it earned from operators who depended on it for survival. The LCC-1 demonstrated fuel efficiency superior to conventional vehicles of comparable payload capacity, a critical consideration for Arctic operations, where fuel delivery represented a major logistical challenge. The electric hub motors required minimal maintenance compared to complex mechanical drivetrains, reducing the specialized technical support needed for remote operations. The vehicle's ability to operate continuously for extended periods without mechanical breakdown proved that electric drive was the superior alternative. The LCC-1's validation on Greenland's unforgiving ice sheet opened possibilities that extended far beyond the original Arctic transportation challenge. For an innovator of LeTourneau's vision, the successful 16-wheel prototype represented not an achievement, but a foundation. The proven concept could scale to dimensions previously considered impossible, limited only by engineering audacity. The LCC-1 had conquered the ice, but for a man like Tourneau, proof was just the beginning. The Army didn't just want a train, they wanted a Leviathan. The Army Transportation Research and Development Command issued its most ambitious contract in 1958, build the TC-497 Mark II, a land vehicle that would dwarf every terrestrial machine ever conceived. This commission represented more than an engineering upgrade from the successful LCC-1 prototype. The specifications demanded a quantum leap in scale that would push industrial manufacturing capabilities to their absolute limits, while creating the largest land vehicle in human history. The TC-497's power system embodied LeTourneau's philosophy that conventional limitations existed only in the minds of conservative engineers. 4 solar Saturn gas turbine engines, each producing 1,170 horsepower, would generate the electrical power required to drive the massive vehicle. These aircraft-derived turbines offered superior power-to-weight ratios compared to conventional diesel engines, while maintaining operational reliability in extreme cold, where standard internal combustion engines faltered. The vehicle's dimensions defied conventional understanding of land-based transportation. Stretching nearly 600 feet from nose to tail, the TC-497 exceeded the length of many naval destroyers, while maintaining the structural flexibility required for ground operations. The modular design incorporated 12 separate cargo sections, capable of carrying massive loads across the most challenging terrain. This configuration allowed the vehicle to articulate through uneven surfaces without the structural stress that would destroy a rigid frame of comparable dimensions. The crew control car represented a masterpiece of mobile engineering architecture. This self-contained command center housed sleeping accommodations for 6 crew members, a fully equipped galley for meal preparation during extended missions, and navigation systems designed for Arctic operations, where traditional landmarks were non-existent. The environmental systems maintained habitable conditions regardless of external temperatures, creating a mobile sanctuary. It was even designed to be nuclear fallout-proof, a stark reminder of the apocalyptic stakes that had greenlit its creation. This self-contained unit could sustain human life during weeks-long supply missions across the Arctic wilderness. LeTourneau's electric hub motor technology reached its ultimate expression in the TC-497's drivetrain configuration. 54 individual wheels, each containing its own electric motor, provided unprecedented traction and flotation characteristics across snow, ice, and tundra surfaces. The distributed power system eliminated single points of failure that had plagued conventional vehicles, ensuring continued operation even if multiple drive units failed during critical missions. Each hub motor delivered precise torque control, allowing the massive vehicle to navigate terrain features that would immobilize lesser transportation systems. The engineering challenges inherent in constructing such a massive vehicle pushed LeTourneau's Longview, Texas manufacturing facility beyond all previous capabilities. The assembly process required custom tooling designed specifically for components that exceeded standard industrial dimensions. Massive cranes positioned sections weighing tens of thousands of pounds with millimeter precision, while specialized jigs maintained structural alignment across the vehicle's extraordinary length. The electrical systems alone required miles of specially insulated wiring designed to function reliably in Arctic conditions. The complexity of coordinating 54 independent drive motors through a single control system presented challenges that pushed 1950s electrical technology to its limits. Each hub motor required individual control circuits that could respond instantly to operator commands, while maintaining synchronized operation across the entire vehicle length. The control systems incorporated feedback mechanisms that adjusted power distribution based on load conditions and terrain requirements, creating a primitive but effective form of computerized vehicle management decades before such technology became commercially available. The completed TC-497 emerged from the Longview Assembly Facility in 1961 as a testament to American industrial capability during the Cold War era. Rolling into the Texas sunlight for the first time, the massive vehicle was a monument to engineering audacity, proof that manufacturing excellence could redefine the boundaries of technological possibility. The land Leviathan represented the absolute pinnacle of ground-based transportation, a mechanical achievement that would have seemed impossible just a decade earlier. Following its delivery to the Army in March 1962, the vehicle prepared for operational trials that would determine whether LeTourneau's vision could fulfill its audacious promise. LeTourneau had built the ultimate ground vehicle, But at the exact same moment, a new machine was taking to the skies, one that promised to make the very ground he had conquered completely irrelevant. The Sikorsky S-64 Skycrane carved through Texas airspace with skeletal precision, its ungainly frame and exposed fuselage embodying a transformative approach to cargo transportation that threatened to render ground-based logistics obsolete. While the TC-497 demonstrated the ultimate expression of terrestrial brute force, this aerial machine promised to bypass terrain entirely through three-dimensional mobility. Igor Sikorsky's vision for heavy-lift rotorcraft emerged from his recognition that military logistics faced constraints that conventional thinking could never overcome. The Russian-born engineer who had pioneered practical helicopter flight understood that a true leap in transportation required abandoning surface-based movement altogether. His Skycrane concept eliminated the passenger compartment, creating a flying crane optimized purely for cargo handling. The aircraft's twin-engine configuration and sophisticated rotor systems could lift external loads weighing up to 10 tons, while maintaining deployment options impossible for any ground vehicle. The military doctrine evolving around rotorcraft represented a fundamental shift in strategic thinking. Air mobility promised to transform military operations by delivering precise cargo placement, bypassing terrain obstacles, poor weather, and enemy-held routes. A single helicopter could access locations that would require massive engineering projects to reach with conventional vehicles. The Skycrane could deliver construction materials directly to mountain peaks, isolated islands, or Arctic installations without the infrastructure that ground transportation demanded. The logistical mathematics favored aerial solutions. Where the TC-497 could haul 150 tons across Arctic terrain at speeds averaging 12 miles per hour, the Skycrane delivered smaller, precisely targeted loads at cruise speeds exceeding 100 miles per hour. The helicopter's operational radius allowed multiple delivery missions from a single forward base, while the land train was tethered to supply lines stretching hundreds of miles across hostile territory. The economic calculus also favored the helicopter. The TC-497 demanded specialized maintenance facilities, trained technical personnel for its complex electrical systems, and consumed massive amounts of fuel from its 4 gas turbine engines. Each Arctic supply mission required weeks of preparation, with substantial risks of mechanical failure. The Skycrane, by contrast, operated from conventional airfields, utilized standard aviation maintenance procedures, and completed supply missions in hours rather than days. Heavy-lift helicopters offered deployment flexibility that addressed the military's evolving requirements. The Cold War's tactical landscape increasingly demanded rapid response capabilities, a doctrine for which massive, sustained logistics vehicles were ill-suited. Helicopter-based supply systems could establish forward operating bases quickly, support mobile military units across varied terrain, and provide emergency resupply capabilities that ground vehicles simply could not match. Pentagon procurement officers found themselves evaluating competing technological philosophies. The TC-497 embodied the industrial age concept that bigger machines solved bigger problems through superior payload capacity and mechanical reliability. The Skycrane represented the emerging aerospace age philosophy that speed, flexibility, and technological sophistication provided tactical advantages over raw capacity. Each approach demanded substantial financial commitments that would influence military logistics for decades. The Army Transportation Research and Development Command faced a strategic decision. LeTourneau's land train offered proven electric hub motor technology scaled to unprecedented dimensions. Sikorsky's helicopter provided aerial capabilities that eliminated many logistical problems entirely by transcending the geographic constraints that made Arctic ground transportation so challenging. The choice represented more than equipment selection. It would establish the fundamental approach to military logistics in hostile environments. This convergence was not limited to the military. Commercial helicopter operations demonstrated growing capabilities for construction projects, oil field support, and emergency services. The aerospace industry's rapid advancement promised continuing improvements in rotorcraft performance. while ground vehicle technology was approaching fundamental physical limitations imposed by terrain and mechanical complexity. The shadow cast by rotating aircraft over LeTourneau's mechanical masterpiece represented more than technological competition. The Skycrane embodied a paradigm shift that questioned the basic assumptions underlying ground-based transportation, while the TC-497 represented the ultimate refinement of terrestrial logistics. The helicopter offered transcendence of the very problems that made such massive ground vehicles necessary. Two futures for military logistics now lay before the Pentagon. One future was LeTourneau's unstoppable ground force, offering proven capacity. The other was Sikorsky's aerial mobility, promising a new kind of warfare. The land Leviathan was ready, the Skycrane was proven, two competing futures for military logistics had arrived, and the Pentagon only had the budget for one. The Arizona desert surrounding Yuma proving ground stretched endlessly under the harsh sun of 1962, its barren expanse providing the perfect testing environment for the most ambitious land vehicle ever conceived. The TC-497 Mark II had finally arrived for its official military evaluation, its massive bulk casting shadows across the desert floor. Yet beneath the confident exterior of this engineering marvel lay an uncomfortable truth. The world had moved on. The early 1960s unleashed a fundamental transportation of American military doctrine. President Kennedy's strategy of flexible response demanded rapid deployment capabilities to address global conflicts. The emerging crisis in Southeast Asia required mobile forces capable of quick insertion and sustained operations in jungle environments, where massive ground vehicles were not just impractical, but a liability. The Pentagon's procurement priorities had shifted decisively toward air mobility assets that could protect American military power with unprecedented speed. This strategic evolution rendered the TC-497's impressive capabilities increasingly irrelevant. The vehicle's design philosophy, rooted in the massive logistics requirements of Arctic DEW line construction, addressed challenges that belonged to an earlier era. While the land train represented the ultimate expression of ground-based cargo transportation, the Army's operational requirements had evolved towards systems that prioritized tactical flexibility over raw payload capacity. The testing protocols at Yuma confirmed the TC-497's remarkable engineering. The massive vehicle traversed desert terrain with mechanical precision, its 54 electric hub motors providing traction that exceeded specifications. The gas turbine power plants operated flawlessly despite extreme temperature variations, and the electric drivetrain delivered superior fuel efficiency. The modular sections articulated smoothly over uneven surfaces that would have destroyed conventional vehicles. Every technical specification was met or exceeded. Yet these impressive achievements occurred within a strategic context that had fundamentally altered since the project's authorization. The bureaucratic machinery in Washington had already reached conclusions that rendered the test results academically interesting but operationally irrelevant. Military budget allocations reflected the new emphasis on helicopter-based logistics. The TC-497's fate had been determined in Pentagon conference rooms, where strategic doctrine trumped engineering excellence. The cancellation order arrived with impersonal, bureaucratic efficiency. Years of development, millions in research funding, and the industrial expertise of America's most innovative earth-moving manufacturer were dismissed with administrative finality. The TC-497 would never revolutionize Arctic logistics because the military no longer required revolutionary Arctic logistics. The strategic landscape had shifted beneath the vehicle's massive wheels. The aftermath of cancellation transformed the desert proving ground into an industrial graveyard. The TC-497 sat motionless under the relentless Arizona sun, its sophisticated systems gradually succumbing to environmental conditions it was never built to endure. Sand infiltrated the precision machinery, while extreme temperature cycles stressed components designed for the Arctic. The world's largest land vehicle became a monument to technological obsolescence. The year 1969 delivered twin blows. Robert Gilmore LeTourneau, the visionary whose electric hub motor concept had made the massive vehicle possible, died at 80, taking with him the passionate, institutional force that had driven the project. That same year brought the final bureaucratic decision to dispose of the TC-497 as surplus military equipment. The dismantling process reduced years of advanced engineering to scrap metal. Cutting torches methodically destroyed the sophisticated systems that had demonstrated such promise. The story appeared to conclude with definitive finality, a brilliant engineering achievement rendered obsolete not by a better machine, but by a different strategy. The creator was gone, his creation was destroyed. By every measure, the story was over. Or was it? Because halfway across the world, in the one place on Earth as hostile as the Arctic, LeTourneau's failed idea was about to be reborn. Deep within the Pilbara region of Western Australia, copper and iron ore deposits demand extraction on a scale that dwarfs conventional industrial operations. Explosions fracture mountainsides into manageable fragments, creating terraced benches that descend into the Earth's crust. But the true marvel of this operation reveals itself in the vehicles that transport these materials at a scale that defies conventional logistics. These are the true titans of the Earth, machines that render ordinary trucks as mere toys by comparison. A single Komatsu 980E5 ultra-class haul truck towers above the mine floor like a mobile building, its payload capacity exceeding 400 tons. The vehicle's dimensions command respect, standing over 20 feet tall, with tires that cost more than luxury automobiles. Yet beneath this impressive exterior beats a technological heart that traces directly back to the electric hub motor concepts pioneered by R.G. LeTourneau decades earlier. Modern ultra-class haul trucks employ diesel-electric powertrains that are the direct evolutionary descendant of LeTourneau's concept. A massive diesel engine serves as a generator, producing electrical current for motors mounted at each wheel. This technological DNA flows through corporate acquisitions and patent transfers that preserve the essential innovations from the TC-497. The fundamental architecture remains unchanged from the system that powered LeTourneau's machines across Greenland half a century earlier. The advantages that made LeTourneau's concept revolutionary in the 1950s are indispensable in modern mining. Electric motors deliver immediate torque, allowing operators to maintain precise control over vehicles whose gross weight approaches 1 million pounds. The regenerative braking that seemed ingenious in the Arctic becomes essential in mining, where loaded trucks descend steep grades that would destroy conventional braking systems through heat generation alone. The scale of modern mining operations is the ultimate vindication of LeTourneau's philosophy that there were no big jobs, only small machines. While the TC-497 was an extreme response to an Arctic problem, today's haul trucks address material movement requirements that dwarf even the most ambitious military supply operations. Mining companies that once relied on fleets of smaller trucks discovered that electric ultra-class vehicles provided superior ton-mile economics despite their enormous initial costs. The reliability that was attractive for the Arctic proved essential for mining, where vehicle downtime translates into production losses measured in millions of dollars. The electric drivetrain technology now enables fully autonomous operations, with computer-controlled fleets operating continuously in the Pilbara's remote mines. Their precise electric motor control providing the reliability necessary for unmanned operations. LeTourneau's vision has been ultimately vindicated. The electric hub motor concept that military planners dismissed as obsolete now powers one of the largest land vehicles ever built, moving mountains of material across every continent, their reality exceeding even LeTourneau's most ambitious dreams. The TC-497 Overland train stands as a monument to innovation's unpredictable path. Its core technology, dismissed as obsolete by one era, re-emerged decades later to power the largest land vehicles on Earth. LeTourneau's electric wheel concept proves that a transformative idea can outlive its original purpose, finding its true calling in applications far removed from its creator's intent. The Overland train's legacy is not one of failure, but of patience, a testament to engineering that was not wrong, merely early. Today, as autonomous mining fleets move mountains with that same fundamental technology, the vindication is complete.